2-minute anaesthesia flow. As with all physics topics, there's a range of key definitions. These include fluid, substance that continually flows under applied shear stress, can be liquid or gas. Volume, three-dimensional measure of the area a substance occupies. Flow, quantity of fluid passing a point per unit time, i.e. litres per minute. Density, measure of a substance per unit volume. Viscosity, measure of the ability to resist deformation by external forces. Newtonian fluid, fluids with constant viscosities. Flow can be turbulent or laminar. Laminar flow, within a tube molecules move in parallel. The molecules moving in the centre of the tube move faster than those at the edge, and this is due to frictional forces. Laminar flow is predictable, and therefore we can use equations to determine the flow rate. Laminar flow in Newtonian fluids, i.e. fluids with a constant viscosity, is governed by Brussel's law and Hagen-Brusel equation, as shown at the bottom. So flow is equal to pi multiplied by the pressure difference by the radius to the power of 4, and inversely proportional to 8 over viscosity of the fluid and length. So flow is proportional to the pressure difference across the tube and the radius. In laminar flow, there's a linear relationship between pressure difference and flow. As the pressure difference increases, the flow increases. As the resistance increases, the gradient of the line reduces. Clinically, why is this important? So you have faster flow down a large cannula. Large ET tubes will result in a reduction in pressure for a given tidal volume. And Heliox. This is a 70-30 mixture of helium and oxygen, and due to the lower density can result in a reduction in work of breathing, which is important in asthmatic patients. Turbulent flow. So most flow in real life is turbulent flow. Turbulent flow is disordered. Particles move in different directions, forming swirls and eddy currents, as shown in the diagram. Therefore, formulating an equation for this is difficult, and because it's unpredictable. The relationship and pressure difference in flow. Flow is proportional to the square root of the driving pressure. In other words, as the pressure gradient increases, flow also increases, but also in a non-linear relationship like laminar flow. Resistance also increases in proportion to the flow rate. Reynolds number. This value, when calculated, predicts if flow is likely to be laminar or turbulent flow. A value of less than 2000 is suggestive, likely that it's laminar flow. Greater than 4000 turbulent, and between 2 and 4000 transitional. The equation at the bottom denotes how this is calculated. Density multiplied by velocity of fluid times by diameter of tube over viscosity of fluid. Turbulence is more likely with increasing velocity, density and a wider tube. 3 key principles. Bernoulli principle. Increasing velocity of moving fluid results in a simultaneous reduction in pressure, i.e. a constriction of a pipe. In order to maintain the same flow, there's an increase in velocity and reduction in pressure. The Venturi effect uses the Bernoulli principle, i.e. this reduction in pressure allows entrainment of gas into the pipe. This is used for the Venturi mask and jet ventilation. And finally, the Quando effect. A fluid or gas stream will hug a curved surface, and this is important for the Nuffield in a ventilator. Venturi valves deliver a set concentration of oxygen to a patient. They work by passing 100% oxygen through a constriction, allowing entrainment of air by the vents. The degree of entrainment is controlled by 2 factors, the size of the vent and the oxygen flow rate, and this is independent of the patient's minute ventilation. Assuming all of the oxygen takes part in the flow rate, it's then possible to calculate, using an equation, the amount of air entrained as shown. Once you have this value, you can add it to the oxygen flow rate to determine the total flow rate. The table in the top right corner shows for the FiO2 the ratio of air to oxygen. It's important to know, as the FiO2 increases, the total gas flow rate reaching the patient decreases. This is important. For example, for 60% Venturi, if the wall oxygen is set at 15 litres, this gives a total flow rate of 30 litres, and this may only just meet the patient's peak inspiratory flow rate requirements. And therefore, if the higher, you'll get additional inhalation of air and thus reduction in FiO2 delivered to the patient.